In this video, we're going to continue our discussion on graph theory, look at some special graphs, including the complete graph and the complete bipartite graph, and then we'll look at some networks and doing network analysis in Mathematica. First, though, we need to define a degree. So the degree of a vertex is the number of edges which are incident to it. Here you can see we have the vertex V, and there are 1, 2, 3, 4, 5 edges incident to it, so the degree of V is 5. Now, adjacency is a term used for two vertices, and incidence is a term used for an edge and a vertex. So we'll keep that in mind as we go through the rest of the discussion. And our first topic is special graphs. So one of the first special graphs that come up is the complete graph. The complete graph is one in which every vertex is adjacent to every other vertex. Here on the left, if we look at our vertices 1 through 5, we see that 1 is connected to 4 and 1 is connected to 3. Every pair of vertices defines an edge. We denote the complete graph as K5, and so the complete graph on 5 vertices has a bunch of edges. We can count them if we wanted to, but we could also count them in a smart way, which generalizes nicely. So there are 5 choices for the first choice of our vertex. And then if we want to pick a second vertex in our pair, there are now 4 remaining vertices because we can't choose the same vertex twice. So we multiply by 4. Now that we've done this, we need to be careful that we don't double count, because if we pick 1 and then 2, that's the same thing as if we picked 2 and then 1. The order doesn't matter. So since each pair of edges, or each pair of vertices shows up twice, we divide by 2, so this gives us a total of 10 edges. Now in the complete graph on n vertices, there are n ways to choose the first vertex. And now when we choose the second vertex in a pair, there are only n-1 remaining vertices. And again, we don't want to double count because the order doesn't matter. So we divide by 2, and that's the number of edges in the graph. This is the maximum number of edges in a graph. And the complete graph contains that maximum number. So what's the degree in a complete graph? If we look at vertex 1, we see that it has degree, in our small case of K5 here, we see that it has 4 edges incident to it, so the degree is 4. In general, though, if each vertex is adjacent to every other vertex, and there are n vertices, then that means that the degree is n-1 for every vertex. So the degree is constant on all vertices. The second type of graph that we'll consider is the complete bipartite graph. Here, instead of considering every possible combination of vertices as an edge, we instead place the vertices into groups. And the vertex is adjacent to every vertex in other groups, but not to any other vertex in the same group. So here in group 1, you see that the black vertices are not adjacent to each other. In other words, this edge never happens, so that doesn't happen. And the same for the red vertices. But every black vertex is adjacent to every red vertex. If we look at the degrees, we see that every vertex in group 1 has degree 3, so these red lines are just to help us count and to group the edges which are adjacent to each vertex. And we see that group 1 vertices have degree 3 and group 2 vertices have degree 4. So obviously we can't come up with a constant degree for the graph like we did in the previous case in the complete graph. Instead, we'll look at the average degree. So we count that in the following way. We have 4 group 1 vertices, each with degree 3, and we have 3 group 2 vertices, each with degree 4. And we divide this by the total number of vertices, which is 4 plus 3. That's group 1 plus group 2. So this is 24 over 12, or 7, which is approximately 3.4. So that tells us that the average degree is 3.4. Now the complete bipartite graph in this case is denoted as follows. We use K because it's a complete graph, and then we have the group sizes, so 4, 3. Now we can have more than 2 parts. We can have 3 parts, for instance. So here we have added this green set of vertices and then added a bunch of green edges. Notice that when we add the green vertices, they are all adjacent to both the red vertices, so we come here as well as all the way back over here to the first group. So that's why each one has degree 4 plus 3 is 7. So now we compute the average degree by looking at the total number of group 1 vertices, as if we use the same labels as before. So this would be 4 of those plus 4 black vertices with each with degree 5, and 3 red vertices each with degree 6, and 2 green vertices each with degree 7. And we divide by 4 plus 3 plus 2. So that is 52 over 9, or approximately 5.8. And I should note that this graph is labeled in the following way, K4, 3, 2, since we now have a group of size 4, a group of size 3, and a group of size 2. As you can see, adding more groups of vertices to the graph makes the graph more complex, and it makes it more challenging to answer what the average degree of the graph is. So we'll look to Mathematica to answer those hard questions for us, and we'll go there now to see how to do that. To define the complete graph, it's actually easier than defining a graph with an edge list. So when we're defining a complete graph, we know that we're going to use every possible combination, so there's no need to supply the number of edges. We just, in fact, give it the number of vertices, and it makes the graph for us. So we'll set G equal to our graph, and we type complete graph, and then give it 5 vertices. And this is the graph that we saw before. This is the complete graph on 5 vertices, but maybe we want 15. And you can see the structure holds, so you can see that it's very regular, very predictable. Now we said that the degree is constant, so we can ask what the vertex degree is of, say, and we're working with our graph G, so we want to know what the degree of vertex 2 is. It's 14. The degree of vertex 3 is also 14, and so on. So that's exactly what we expected. It's 1 less than the number of vertices. Then we said that we had a complete bipartite graph defined with, in a similar way, just with groups of vertices. So let's let G2 be our new graph. We again type complete graph, but now we give it new parameters. So we give it a number of vertices in each group. So we had 4 and then 3. This should be in curly braces. And there's the graph that we already saw. And we can add that last set of 2 vertices by making a new set, and we could add another one. We could make another set of 3 vertices, and you see it gets pretty complicated very quickly. So this is how to create the complete graph and the complete bipartite graph in Mathematica. We just have to give it the number of vertices that appear in the graph, and Mathematica does the rest for you. So let's now take a look at some networks. So now that we have seen the complete graph and the complete bipartite graph, let's take a look at networks. Networks are much less predictable than the graphs that we've looked at previously because there's so much structure in those first 2 graphs. Networks are usually used, or networks or graphs I should add, are basically the same thing, it's just a different name. And networks are used to model a lot of real-life phenomena, such as travel problems, or transport problems, or social networks, or electrical circuits. And that's why these things are much less structured than the complete and complete bipartite graphs. As you can see in this graph on the left, we don't know what the average degree is. It's probably not it's definitely not complete graph, and it's probably not complete bipartite. But we have one vertex of degree 1, a vertex here of degree 2, and here a vertex of degree 1, 2, 3, 4, 5. So there are a lot of different degrees here, and we'd like to maybe know what the average degree is. To do that in a network, we can use linear algebra. So the average degree is approximated by the largest eigenvalue of the adjacency matrix. So if we have a graph and we know what the adjacency matrix is, we can compute the largest eigenvalue and choose that as the approximation for our average degree. So in this case, maybe this is a social network, and we'd want to know what's the average number of friends that people have. Well, we could compute the average degree because that would give us the average number of friends in a social network. And computing the largest eigenvalue would do that for us. Another question we can ask is, what is the maximum flow between 2 vertices? So here the blue vertex is the source and the red vertex is the target. And you can think of this as the largest amount of something you can send through a network without having any backup or any traffic jams or any overflow. So let's look at what this maximum flow is for this graph. We can pick any one of these 3 edges coming out of the source node. So let's say I pick this one, and then maybe I go down this way, and then up this way, and over here, and down to the target. So that's one way to get to the target from the source. It turns out that if we look at this a little more closely, a little more carefully, we see that the maximum is 3. The maximum number of simultaneous paths to get from the source to the target is at most 3 because there are only 3 edges coming out of the source node. But if we look at it even further, we see that we can't go down this edge at the end because that's not connected at all to the source. So we have to use these 2 edges coming in right here. So the one that we already used and this one. So in fact, the maximum is at most 2. So let's see if we can find another one to reach at least 2. So let's go down this one. And then we're stuck because we can't reuse this edge because that one's already used. That would result in an overflow. So we're stuck, we can't use that one. So let's instead try this one. We go here, and of course we can't go down the other edge because that's just a dead end, but we can go down this one and then down this edge to the target, and those are our 2 paths going from the source to the target. So the maximum flow is 2. Now in this graph, was pretty easy to find the maximum flow by hand, but for larger graphs you can imagine that this can be really tricky, keeping track of which edges have been used and which haven't. So we're going to look to Mathematica to solve this problem for us. To get a network in Mathematica, we'll just use a random graph. So we'll type G is a random graph. And now we put in curly braces the number of edges. So we'll make or the number of vertices. So we'll say 100 vertices and 230 edges. When we run this, it'll give us a graph with 100 vertices and 230 edges. So here you can see it's not structured. It doesn't seem to be any underlying structure at all. Certainly less structured than the previous graphs that we saw with the complete and the complete bipartite graphs. So one way to compute the average degree, maybe we want to know what the average degree here is. One way to compute that is to go through all the vertices and ask what the vertex degree is. So we're working with the graph G, and we want to know what the vertex degree of the first vertex, or what the degree of the first vertex is. We see that it's 7. Okay, so there's 7, and then we check 2, and that's 4, right? And 3, that's 3. So we could go through all the vertices like this and find the average. Of course, that's much less efficient than doing it through the method that we now know of, using the eigenvalues. So let's get an adjacency matrix. I'll call it A. Get the adjacency matrix of the graph G. And this is the sparse array that we've seen previously. Now we can ask for the eigenvalues of this matrix. And Mathematica returns this output. So it says root of these really big numbers with these strange symbols and all this other stuff that it cuts out. So this is not very helpful. I don't really know what this means. I can't tell what the average degree is or find the largest eigenvalue. So we'll ask for a numerical approximation. And now we see that the average degree is 5.64 because that is the degree of the largest eigenvalue in its list of eigenvalues. So let's maybe find the maximum flow from 1 to 100 here. So let's say we want to find the maximum flow, and we can just ask Mathematica the question, what's the maximum flow from 1 to 100? That's from vertex 1 to vertex 100. And it says that there are 3 different ways to do that. So maybe we don't want just the number, maybe we want a graph. So we can ask for find maximum flow, add one parameter called flow graph, and that now highlights it, so it returns the original graph, but it highlights the edges which are used in the maximum flow. So this does all of the work that we did, tracing out the individual flows in order to find the maximum flow. Alternatively, we can ask for just the edge list. And here it returns all the edges which are used, but maybe we want to just consider that subgraph. So this is a list of edges, but that's what defines a graph. So I'll just call this a new graph. And we just add in, so this is how we define a graph originally. So we say graph and then put in the brackets a list of edges, but that's what this is. So when we run this, we get this graph, which is much smaller than the original, and we can turn on vertex labels. so that we know which one is 1 and which one is 100. And when we run this, we see that we're going from this vertex 1 over to vertex 100. So that is how to find the maximum flow, either the flow value or the flow graph, within a larger network using Mathematica. So in this video, we've looked at complete graphs, complete bipartite graphs, and then we've also looked at networks and network analysis using Mathematica.